in the last lecture we started looking at something called the Lie derivative. That's a way to take the derivative of a vector or a vector field when you have a reference vector field in place. That allows you to tell you, it gives you a canonical way to move vectors around on a manifold. So last lecture we got so far as to write down the definition. So, given two vector fields, x and y, on some manifold M, x being the reference vector field, we can define the Lie derivative of y with respect to x according to the following formula. So I'll explain it in words, draw a picture. Maybe I draw the picture and then explain it in words. So the picture we have in mind here is we have some reference vector field here, and we have some flows along these vector fields. There's some vector field on our manifold. This is the flow for that reference vector field x. And then we have some point that we're interested in. I'll put the arrows the other way for the moment. We have some point that we like, x. Let's call it x. I'll put x over here so we've got enough space. So we have some point in the manifold that we like. And then we have another point over here, x prime, which is equal to flow that point for a little bit along the vector field big X. There's two nearby points and they're on an integral curve like this. And then we have ourselves a vector at this point here. That's the vector y at x. And then over here, I mean, the vector field y is defined everywhere on the manifold, so there's going to be a vector over here. That's y defined at sigma epsilon of x. And the objective is to compare these two vectors. We want to compare this vector with this vector, and without the data of this reference field, we would have no canonical way to do that unless we had some Riemann structure on this manifold or something else. Maybe it's a bundle or something. There are other ways to do it, but this is the way we're doing it when we have access to a second vector field x. What we do is we move this vector along this integral curve here, and we have a canonical way to do that. That's the push forward. And then, so we move this guy along, and there's it. That's what we get there. We push forward y, and we get this new vector here. And the nice thing is this new vector is actually has the same base point x. Maybe I'll render this in some different colors. That's the red vector is y at this other location. And over here we have the yellow vector is our original y, and then we not parallel transport, we push forward the red vector here to x. Now we have two vectors at the same point on the manifold. We're entitled to take their difference, which is exactly what we do here. And then we're also entitled to let epsilon go to 0 and then divide by epsilon. Everything is good. We have ourselves a well-defined operation, which we're calling the Lie derivative. Now, that's all very well and good, right? We've drawn some pictures, we've made a definition here, but how useful is this in practice? Well, it depends on how well you can actually compute this thing here. And to do that, we're going to need coordinates. Have to at some point go to coordinates. So the task for today is to look at this expression in coordinates, work out how to calculate it, characterize its properties also of this operation. And then finally today we're going to generalize all this stuff to one forms, n forms, and then mixed tensors. Okay, a little exercise to get you warmed up in this business. Show that you can define the Lie derivative in various other ways. For example, you could instead define the Lie derivative this way by pushing forward the vector at x rather than pushing forward the vector at sigma epsilon x. Got to argue these are the same thing. So you think about that. Now our next step is to write down this definition in terms of coordinates. Actually calculate this thing. So let's specialize to a chart. Just going to write out everything now in terms of coordinates. We need a chart for that. We're going to name the coordinates x mu, and now we're going to have to write down our vector fields in terms of these coordinates. So in terms of the coordinate basis, our vector field x is written as x mu d dx mu, and y similarly. And now we have to look at that definition and work out all this stuff in terms of coordinates. So we've got several moving parts in this definition we have to keep track of. We have to write this out in terms of coordinates. Well, that's the easiest bit, right? That we've done, more or less. And then we have to write out the vector field at the location sigma epsilon x pushed forward to the location x in coordinates. So we're at least going to need to be able to write out what is sigma epsilon x. We're going to need to be able to write out the push forward, and we're going to need to write out a y in coordinates at this other location. So let's get started on that. The first thing we'll need is what is the flow sigma epsilon x? What's that actually equal to when epsilon small? Well, that we can work out just by solving the integral curve equation to first order by iteration, or expanding the exponential if you like. So to first order, when you flow the point x to under the vector field x for a bit, you end up at x, obviously, right? You started at x, and you've got to do some, you're going to move away from it. And to first order, you end up with just adding the components of the vector field to x like that. It's also important to have the inverse of this flow, write that out, and so there's two ways to work that out. Either you just expand this to first order in epsilon, or you work out what the inverse map is to take this point back to x mu to first order. So in either way, we get the same answer. And now we've got some more parts that we can look at. We can start looking at what's x at sigma epsilon x, what's y at sigma epsilon x. Well, we could write it out in terms of components. We have this expression here. So it's located at sigma epsilon x. Well, let's just use, we're going to do everything to first order because higher order terms will vanish ultimately. So we're going to substitute that expression already in the argument of y here. And, well, we have a basis. And it's slightly awkward when we've got lots of x's around. So my solution notationally was to do this. So there's something really awkward about writing d dx mu at the point sigma epsilon of x. So we're going to use this notation to avoid doing that. It's super confusing otherwise. So we want to get everything in terms of to first order. We want to understand everything here to first order. So there's two things we need to do. We need to, this is just some a vector value function, right? Some function on the chart. We're going to express that as a Taylor series. And over here we've got this basis vector, but not at the right location. To deal with that, we're going to have to push forward this sigma minus epsilon x. But let's do each part in turn. So let's first Taylor series this thing in up here. Okay, that's kind of pretty easy, right? We got a I don't want these, I'm going to want to use the index nu. I don't want to exhaust all my indices too quickly. So I'm going to do something that I hope is fairly obvious what I mean here. I'll put underlines on it. That should work. That should make it work. I don't want to write indices for the argument here. That's just going to lead to problems. And then we do things just to first order here. And we end up with this expression. Oh yeah, there's more to it, right? Dot, 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 dot. We're part of the way there. Now we've got to express our basis vector E mu, or we've got to move our basis vector E mu located at sigma epsilon x. We've got to get it via the push forward So if we have like some z some vector at sigma epsilon x, when we push it forward, we're going to get a different vector. We have a rule for how to do that. That's a star. Namely, you work out the first derivative matrix of this map here and put it inside there. All right? If we work that out, we have a formula for sigma minus epsilon. Plus dot dot dot. Something's wrong. I think I've got my indices the wrong way around. That looks a bit better. For this we do, for the Jacobian. So this is defining the coordinates x prime nu. So when you work out the thank you. Thank you. That's what I was doing wrong. Okay, now I think everything works. So if we put this together now with the expression we have up there, we should have in components, if everything works out, the expression for y pushed forward from the position sigma epsilon x to x. So let's give it a go. Minus it. Here is news. So we've got multiple terms here. The origin of this term is from Taylor expanding y at the wrong location in terms of the right location. And the origin of the second term is this push forward. And we're going to expand this to first order and epsilon. So we're going to get 3 terms, right? Because you never get the epsilon squared term. So you get x d mu d nu d mu y mu blah, minus y d mu dx nu. So you'll learn to recognize this combination in future. Oh, and I forgot the order 1 term. put the order 1 term in here. Oh no, I had it in there, didn't I? Ugh. Okay. So when we subtract off in the definition of the Lie derivative, I still have it here. No, I erased it. When we subtract off the value of the vector field at x, this just cancels this order 1 term. And when we divide by epsilon, that gets rid of the epsilon here. So we have that the Lie derivative of y with respect to x is this expression here. And I must have an error here. That's a new. Yep. There you go. Neato. And this is how you would actually do it in practice, right? If you had a vector field, you'd have specified its coordinates at least in one chart, or at least know how to get the coordinates. And if you had the other vector field y, then you could input these functions and you'd be able to work out the Lie derivative using standard vector calculus. Okay, let's see if I dare to do an example without having tested this before. It's always a dangerous business cooking up an example. Okay. To make things interesting, i.e. not one-dimensional, let's make it a two-dimensional manifold. I'm not going to do it on the sphere, or you could imagine this is a vector field on some chart on the sphere. Now we're going to build some vector fields. I guess x and y is maybe stupid, so we'll just call this y x1 dx2 and x1, oops, x2 dx1. So we've got this vector field here, x. So we're going to see a lot more of this vector field. This is the vector field for rotation. And then y, we need some other vector field. Let's choose x1 squared. Plus x2. Okay, see how bad this can go. So that means that x capital 1 as a function of the argument is minus x2, and x capital 2 as a function of the argument is little x1. Because we're going to need that when we go to this formula here. And similarly, y capital 1 as a function of the argument is x1 squared. And that was, yeah, that's x2. So, yeah, I guess it's probably safer if I just put brackets around everything here so that we don't confuse coordinates with powering. And now we have a couple of derivatives to do. So let's start doing them. In total, we need four objects, right? Mu can run over 1 and 2, and nu can run over 1 and 2. So we're going to need, well, 8 little calculations that we're going to need to do. So x1 is minus x2, dx1 plus x1 ddx2, all applied to x1 squared. So I'm working out the coefficient of E1 at the moment. So we'll open up a curly bracket, and then we're going to subtract off this term here, which is, unbalanced bracket there, minus, same story over here. So y1 is x1 squared, x1 squared, ddx1 plus y2, which is x2, ddx2 applied to all to x1 if we're working out the coefficient of E1. So x1 is minus x2. And there's another term for E2, which I'll leave to you. We'll just do this first one. There's enough going on in there. So here we've got something that we can do now. We've got ddx1, x1 squared, so that's 2x1. So we've got minus 2x1 times x2, and this is just 0. When you differentiate x2 with respect to x1 with respect to x2, you get 0. So that was easy. Minus, do the same thing over here. That's 0, and we get this term here, which gives us minus x2. Plus, and there's something for the coefficient of E2. So there we go, we've got our first Lie derivative example. So I certainly invite you to work out the integral curves for the vector field x. They should be circles around the origin, if I've done it correctly, which I believe I have. And you can then visualize this, the Lie derivative that we just took place here. So let me draw what we've just done. So the integral curves of the vector field x are circles. I hope I didn't mess up that. So the vector field x is this one where the vectors point like so. So that's the integral curves for x. So this is the flow sigma s x. I'll just write it as sigma s. That's the flow there. And we have another vector field. That's the one determined by y. And how do I draw that one? So it's always got a constant y component, but the x component gets sort of parabolic. So it's something like, we've got a different color for y. Let's use red. I think that's what y looks like as a vector field. Because as you go further along the x-axis, the coefficient of the x component gets bigger and bigger. So something like that. I'm not very good at rendering these vector fields. And then this Lie derivative is comparing, say, this vector here with this vector here pushed forward. Under the flow. All right, we have this nice formula for the Lie derivative, but let's make it even nicer. So we're going to exploit notation to simplify that formula, and that will make it easier to remember and also exhibit the properties of the Lie derivative in a much clearer way. So if we have in coordinates now, two vector fields, x on our manifold M, then we're going to define some notation that's very useful for us, namely something called the Lie bracket. So this symbol by itself doesn't mean anything. We have to say what it is. Well, it's a vector field. So I should make that, state that clearly. We'll deduce that it's a vector field, but it's a vector field. So the Lie bracket, what it does is it takes two vector fields and gives you another vector field. And how does that notation work? Well, if it's a vector field, then it must be possible to apply it to a function. That's what vector fields do. And here's the definition. Oops. So this stage, it's totally non-obvious that this thing is a vector field. It's totally not consider it not something you can see immediately that this is at all a vector field. Because we're composing two vector fields, there's going to be second order derivatives, presumably. But for something to be interpretable as a vector field, remember it's got to be a first order derivative. So indeed, you know, the notation and the definition makes it clear what's going to happen. The second order derivatives are going to cancel. So we're going to be left with a first order differential operator, thus justifying that statement here, that it's in the vector fields on M. But let's actually prove that. So if we have some function on the manifold, let's actually work out the right-hand side of the Lie bracket and see what we get, and then we'll get something very interesting. So in components and substituting everything, from the definition, we end up with this lovely expression here. Now everything's functions. Now we have to deploy the product rule, because we're differentiating a product of two functions. And here we're differentiating a product of two functions. So I am going to, no, I'll put it in the intermediate step. It's the first part of the product rule applied to the first term. And then, yeah, I'll put the good stuff first. And the bad stuff second. So that's the good stuff, first two terms there. And the bad stuff are the the partial derivative expressions involving at second order. Okay, the second order partial with respect of f with respect to x, mu, and nu, and correspondingly there's one and the beauty is, of course, this is the coefficients of a symmetric matrix here, x mu, x nu, y nu, and second order partials are equal, and we've got a minus sign. So the second order terms vanish. And we're left with something quite familiar, namely Lxy. So I will leave it like that. Lxy on f, of course. So now we see why we call this the Lie bracket. It's called the Lie bracket because it's equal to the Lie derivative. now we've got this bracket expression. Let's justify the notation of a bracket. So whenever you see something like a bracket, it should make you start thinking bilinear, right? Because when you put a comma traditionally in maths, you have something with two arguments and a bracket and a comma in between the two arguments. You tend to think that it should be bilinear. And that notation doesn't deceive you here. Indeed, it is bilinear. And I'm going to leave that property as an exercise. So show that it's actually bilinear. That's just with respect to the second argument, but of course to be bilinear, you need to be linear with respect to the first argument as well. So that means c1 x1 plus c2 x2 y had better be equal to c1 x1 bracket y. That's the first exercise. Hope that's not too much of a chore. If you just look at the top board there, you can more or less see that that exercise is proved. But I'm a big believer in the benefits of writing out things on paper to internalize patterns of behavior. So I think it's a worthwhile exercise to write that out. Because until you've internalized algebraic manipulations, there's always this transaction cost when you want to do some derivations. You've internalized how to solve a quadratic equation. You've just done it so many times, minus b plus minus square root, blah, blah, blah. And that allows you to mentally skip through steps in a derivation when you've internalized them manually as well as mentally. And if there's just the teeniest transaction cost in thinking through a long derivation, you've got to remember, how do I solve a quadratic equation again? Then when you start to build consequent steps on that, when you try and come up with a conjecture, then these little transaction costs multiply. And so at the end, it's harder and harder to imagine how a calculation will go. So that's why I'm a big believer in internalizing manipulations by repetition, by writing. There's some connection between writing an equation and imagining writing an equation. So there's good studies on this, right? If you learn a musical instrument and you imagine practicing this musical instrument, then that actually delivers benefit to your performance with the musical instrument, even if you never even touch it. So you think about practicing the piano or the guitar or something, then actually this gives you quantifiable benefits when you actually next play the instrument. And maths is no exception. If you write these things down, then that's connected with imagining writing them down, and you'll become quicker at doing derivations. You'll be able to see further into the future in a derivation and know where it's going to go. So even though this is trivial, I want you to write it out. That's why I give you these exercises, to give you that advantage. Skew symmetry. It's also trivial, isn't it? Write it down. The power of writing. And here's a much less trivial one. It's called the Jacobi identity. So that's a pretty important one, the Jacobi identity. Again, it's not that complicated if you look up at the definition of the Lie bracket. But doing the calculation will deliver you benefits. Some other quite interesting properties of the Lie bracket. Here's one that's maybe not particularly obvious, but when you write it out, it becomes obvious. So if you have a function on a manifold and you have a vector field on a manifold, then f times x is just the pointwise product of f and x. So it's another vector field. So the Lie derivative with respect to a function pointwise multiplied by a vector x gives you this object here. Okay. It's not completely clear that that would have happened, but that's what you get. Oh, on y. Now that works. And then if you instead do the Lie derivative with respect to x of f pointwise multiplied by y, and we're going to get a similar expression as well. And I think I can squeeze in the last property here. So the Lie bracket's a vector field. What if we push forward a function? What if we have a function between two manifolds and we push forward that vector field? Well, everything's nice and plays nicely together. The Lie bracket of the push forwards is the push forward of the Lie bracket. So let f be a map between two manifolds, m to n. Then you have the very pleasing formula that if you push forward x and y, the bracket of x and y, that's just the same as if you had pushed forward the vector field separately and then took their Lie bracket. So let's give this Lie bracket a bit of interpretation before we move on to looking at differential forms. What physically is this Lie bracket doing? Well, the answer is it's measuring the non-commutativity of going along two flows. So if you flow along x and then y, and then compare that operation with flowing along y then x, then you may not land at the same point when the vector fields aren't nice and flat. And it turns out the Lie bracket is exactly the thing that tells you the difference between these two actions. So we have two vector fields, and here are the integral curves. Here's some point on the manifold X. We flow for a time epsilon to a point sigma epsilon x. And then we flow for a time tau, delta, to tau delta x. And then you could say, well, I want to understand the difference between first flowing according to sigma and then tau and sigma. So you then flow for a time delta according to tau up here, tau delta, but now on sigma epsilon x. Now, because the vector fields are curved and maybe behaving in a different way far away from x, the action of flowing the point sigma epsilon x for a time delta could be different. You might not end up in that point up there. Similarly, this point over here, that's what you get is when you flow for a time epsilon, the initial point tau delta x, like so. So this is the kind of generic situation you could find yourself in. If you go this way, then this way, you end up at some point. And if you go this way and then that way, you end up in another point, not the same point. Now, if you look at this picture long enough, you can see that they're different. I mean, although it makes no real sense to talk about the difference between these 2 points, in coordinates it does, and when epsilon is small enough, you can draw a vector between these 2 points here. So you wonder, what is this vector that tells us the difference between going first delta then epsilon, and then first epsilon then delta? And so to understand that vector in coordinates, you could expand both the left-hand side and the right-hand side. So that leads us to the following exercise. In coordinates, study to first order in epsilon, first order in delta, but to second order in epsilon delta, the difference between flowing first by sigma then mu, and then first by sigma then tau, and then tau and then sigma. And the exercise is to show that this is equal to none other than epsilon delta, the commutator of x and y, the Lie bracket of x and y, the muth coordinate thereof, plus higher order. So that should be little o epsilon delta. Very interesting connection here between the flows and the Lie bracket. And this connection allows us to deduce something rather interesting. The Lie bracket, or the Lie derivative of y with respect to x, is 0 if and only if these flows commute. quite interesting. I mean, even the fact that this is not 0, only at second order, is not entirely obvious from this picture here. So it's worthwhile doing this. It's just a double Taylor expansion, what you need to do. So there's nothing particularly challenging in this calculation. So that's just x of in coordinates, that's just x nu and then you do another Taylor series with respect to epsilon by flowing according to x. Do the same over here. Then I think it's sort of clear when you look at that the first order terms will cancel, and then you push it through a bit harder and then you get to this result there. All right, we spent a long time now talking about vector fields and Lie derivatives of vector fields. It turns out this Lie derivative operation is pretty useful. We can extend it to all tensors. So as long as you have one reference vector field, then you can define a derivative operation for any mixed tensor. Let's start by doing the Lie derivative for one forms, and then I'll write out basically a definition in terms of a proposition. So if you have your reference vector field x, but you have now a one form, what could it mean, the derivative? Well, we have a reasonable notion of pullback for one forms. So we're just going to replace everywhere where we would have put a push forward with a pullback. So this is now pull back. So that's actually a definition. I like 3 limes to mean equivalent, so that's a definition. So that is one natural way to exploit the idea we had for vector fields and apply it to one forms. Now, what does this mean in components? Well, if we write omega in components now, we can get a component expression for this Lie derivative of this one form. It's exactly the same argument as what I used to get the component form for the Lie derivative of a vector field. It's just that wherever you have Jacobians, you have to put inverse Jacobian matrices, because forms transform differently to vectors. And I will not deny you the pleasure of working out this exercise. Everything's properly contracted there. Yep. So this bit here is just the component form of that. And again, there were 2 steps that went into this calculation. So the first step is working out what does this one form look like at sigma epsilon x in components. And the way to do that is you expand out these functions as a function of x to order epsilon. And that's where the capital X nus come from. And secondly, you have to pull back the one form at this place back to x. And for that you need the inverse first derivative matrix. And then you expand everything to order epsilon. Next one. Next we'll just use this to write out the Lie derivative of a one form. And then we'll immediately generalize to K forms. And then we're almost done. So a consequence of this little exercise here is the expression for the Lie derivative of a one form, namely in components x nu d nu omega mu minus d mu x nu omega mu there we go. That's how you do the Lie derivative of a one form in components. Great, that was the definition of the Lie derivative of a one form. What about a K form? Why stop with 1 when you can go to K? I won't give this to you in components because a proposition that I'm about to write after this will tell you how to do it. So the Lie derivative of a K form, remember that's an anisymmetric function of K vectors. Is, well, we just use the same idea, right? We've got, the idea is you have a reference vector field X, and you have a notion of how to compare a form at two locations on a vector field by the pull back. And we know how to pull back a K form. We have a formula for that. So that's how we're going to do it. So that's one way to generalize the definition. It's exactly the same thing we've been doing the whole time. You have your one form defined in two locations. So ddt at t equals 0 is just that limiting process where t goes to 0. So you could imagine replacing this instantly with limit of 1 over epsilon x with epsilon x, blah, blah, blah. So this is the pull back of the flow with respect to x of the K form differentiate. So that's how you define the Lie derivative for a K form. And you can work out what that means in components if you're extremely interested in writing out lots and lots and lots and lots of components. Or you can take the following proposition as a definition instead, and then work out the Lie derivative. In a much more economical way. So it's kind of clear how to extend this, I hope, to mixed tensors now. So a mixed tensor is a tensor product of some forms and some vectors. And you know how to pull back a form, you know how to push forward a vector. It's kind of clear, I hope, how you would define a Lie derivative of a mixed tensor then, just by combining these two operations. Now, if you like, go ahead and write that definition out. And then, if you do that, then you'll interpret the following as a proposition. But, you know, I'm kind of content to interpret this as a definition. So if you have two mixed tensors, T1 and T2, then the Lie derivative, well, one property of it is that it's linear. Okay, it's one obvious property of the Lie derivative that you ought to have. And the second one, that's the more useful one, is what do you do if you encounter the tensor product of two mixed tensors? And this is what you really need to be able to generalize this notion to anything. If you could somehow calculate this in terms of the Lie derivatives of the constituent factors in this tensor product, then you could bootstrap up the definition we already have for k-forms and the definition we already have for vectors up to a definition for mixed tensors. And indeed you can, and the trick is, not that there's a trick, is that the Lie derivative obeys this Leibniz property that you differentiate the first thing, and then you differentiate the second thing, and the third thing, and so on. So this is true for arbitrary tensors. I'm not going to prove this proposition. Instead, I just like to think of it as a definition and just use it to extend the definition of the Lie derivative to mixed tensors this way. So to deal with your arbitrary mixed tensor, it's going to be the tensor product of some k-forms and some vectors. Yo, a question?
A question about this Lie derivative of the one form.
K-form.
Yeah, no, yeah. On top of that.
Oh, yeah, this one.
Is the derivative acting on both x?
Oh gosh, yeah, the question is the derivative acting on both? Absolutely not, no. Sorry, yeah. That was unclear. Super. So I think we'll stop here. We've finished with our Lie derivatives. We have vector fields, we can differentiate them, we have forms, we have symplectic manifolds, and in the next lecture we're going to learn how to build, using symplectic, the data of a symplectic manifold, vector fields from functions. This is really the most important feature of a symplectic manifold. Given a scalar function on a symplectic manifold, there's a canonical vector that you can associate with that scalar function. And that scalar function is a function on a symplectic manifold is what you interpret as a Hamiltonian in classical mechanics. So given the data of a Hamiltonian, you get a vector field, and the vector field is what generates the integral curves, and the integral curves are what you call trajectories in phase space. So we're going to start doing this huge generalization of classical mechanics to symplectic manifolds in the next couple of lectures. And we have enough data, I think, to get started on that. Good. Thank you very much.